Okay, so now we're going to look at rational functions where the degree of the numerator and the denominator is the same. So what we're going to look at first is the end behavior, and then we'll look at graphing them. So the end behavior when the degrees are the same. So the end behavior is what happens when you look at x going to infinity and negative infinity. So x goes to positive and negative infinity. What happens to y? Okay, so then y goes to question mark here. Okay, so that's what we're looking for right now when the degree is the same. So we can start off with something simple like f of x equal to x over x minus 2. Well, they're both linear functions, so x and x minus 2 are linear functions. The degree of this top is 1, and the degree of the bottom is 1. Okay, so as an example, what we're going to do here is the little trick that I showed you in a previous video to see what happens in the end behavior. We're going to multiply the top and bottom by the same thing, so do nothing rule, just to change the look of it. So x over x minus 2, and we're going to change, so multiply the top by 1 over x, and we're going to multiply the bottom by 1 over x. Okay, so the highest degree on the top here, which happens to be the same degree on both of them. So 1 over x times x, well, that equals 1. 1 over x times x here equals 1. And 1 over x times negative 2, so it's minus 2 over x. Now, when we're looking at around x equal to 0, this is not valid. But when we're looking at large values of x, well, you can divide by large values of x here. So as x goes to infinity here, plus or minus infinity, well, this is approximately equal to, and very closely equal to, just 1 over 1. Because 2 over x is just tends to 0. When you divide 2 by a really large number, it becomes 0, and 1 minus 0 is basically 1. So this becomes 1. Now, when x is positive, this is slightly bigger than 1, because 1 divided by 1 minus a small amount is going to be bigger than 1. When x is negative, well, minus a negative is going to be positive, be addition, so 1 plus a really small number, it's bigger than 1, and the whole thing would be just slightly less than 1. But basically, f of x is approximately equal to 1 as x goes to infinity. So what we have here then is a horizontal asymptote. Okay, so we call it HA for short, is horizontal asymptote of y equals 1, which is that. Okay, this is the y values. So as x goes to infinity, the function tends to approach a y value of 1. So on the graph, you'd have this dotted line here, y equals 1, and out far, well, the function is going to go something like this, and something like this, okay? And we don't know what's happening in between yet because we haven't analyzed that. We'll look at that in a few minutes. Okay, so that is the end behavior of that one. Well, let's try another one. So let's try another example here. See what happens when you have something like f of x equals 2x minus 1 over 3x plus 4. If you use the same trick, well, the degree of the top is 1, the degree of the bottom is 1. So I'm going to multiply the top and bottom by 1 over x. Okay. 1 over x on the top, 1 over x on the bottom. And when you multiply that through, you end up with 2x times 1 over x, it's just 2, minus 1 over x, because you're distributing this into here, over 3x times 1 over x is 3, minus 4 over x. Okay? Now, as x goes to plus or minus infinity again, these pieces here tend to 0. That goes to 0 and that goes to 0 as x goes to infinity. So this basically becomes approximately equal to 2 over 3 as x goes to plus or minus infinity. Okay, because these pieces become negligible. So when x is really large, positive or negative, the function tends to approach y equals 2 over 3. Okay, so therefore we have a horizontal asymptote of y equal to 2 over 3. And graphically, what would this look like? Well, you find 2 over 3 across here, so there's y equals 2 over 3, and then the function would approach that either from the top or the bottom on both sides here, and whatever happens in the middle we're not sure of yet. Okay? So these are two examples where the degree of the top and the bottom are the same, but it's also just when the degree is 1. So we're going to try something a little bit more complicated now, but the same basic idea, and that is for f of x equal to something like, how about negative 3, use a negative here as a leading coefficient, x cubed minus 2x plus 7, say, over another cubic, how about 2x cubed minus 1. So now we have the degree of the top and the degree of the bottom are both 3. Okay, so when we're looking at when x is really large here, I'm going to multiply the top and bottom. Instead of by 1 over x, I'm going to multiply it by 1 over x cubed. So negative 3x cubed minus 2x plus 7 over 2x cubed minus 1 times 1 over x cubed. 1 over x cubed. Multiplying the top and bottom by the same thing here. It's like doing nothing, just changing the look of it. Okay, and when you multiply that in, 1 over x cubed times negative 3x cubed is just negative 3. They cancel out. Negative 2x times 1 over x cubed is going to be minus 2 over x squared. One of the x's here cancels out with one of them in x cubed, and you're left with this. Then plus 7 over x cubed gives you that for the numerator. Now, the denominator, 1 over x cubed times 2x cubed, well, that's just going to be 2. The x cubes cancel out. And then this part here is going to be minus 1 over x cubed. And then as x goes to plus or minus infinity, well, this part, and this part tend to 0. Okay, a constant divided by a really large number gets really small. So that, and that, they go to 0. So you're really just left with negative 3 over 2. And so the end behavior for this one is going to be y approaches negative 3 over 2. So therefore you'd have a horizontal asymptote of y equal to negative 3 over 2. Okay? And basically you see the pattern here. The horizontal asymptote is just the coefficients of the leading coefficients of the top polynomial and the bottom polynomial. As long as the degrees are the same, then you take the leading coefficients and that's your horizontal asymptote. So you don't have to do this every time. It's the same process. In the last examples, well, we had, for this one up here, we had we had 1, and 1 is the leading coefficient, so the horizontal asymptote was 1 over 1, which is just 1. And in this one, the leading coefficients were 2 and 3, and the horizontal asymptote was y equals 2 over 3. So you can jump right to that conclusion now. Okay? And then in this one, you'd have a graph where the horizontal asymptote is down here, y equals to -3/2, and we don't know exactly what's going to happen here, but it's probably going to approach something like that, and we just don't know what's happening in the middle. Okay, so now we're going to look at what it looks like to be fully graphed when these polynomials in the top and bottom are going to be factored.